Thank you a lot for the introduction. Yes, as you say, I'm Renzo Caballero, a Ph.D. candidate from the University of Science and Technology. I'm a Professor who is now unfortunately. And today I will present my work studying the fixed point with the self-repair process 3D printer. So, we will start with the motivation of the work. After I will show some background and our previous work. I will actually present this as this current work, and I will conclude with some final remarks. So we'll start with the motivation. First, some definitions. We say that a system of robots self-assemble when they can assemble and assemble their own parts. They can self-replicate when they can fabricate copies of all its parts, and they can self-repair when they can fabricate copies of its broken parts, or if they can repair them. So, what can be the application of such systems? For example, in the picture here we see the empty quarter in Saudi Arabia and the Bangladesh in South America, which are places where humans can only survive for a long period of time without the correct equipment. So we believe that in order to colonize these kind of places, a community of robots that can replicate and repair themselves is a good candidate. So we can think even a bit further in the sense of the space explorations. Here's a picture of the surface of the moon and the surface of Mars. Here there are extreme scenarios where actually humans can only survive a few seconds without the correct equipment. And we believe that one of the only candidates who can actually colonize places is actually a community of robots with these characteristics, this kind of autonomy, self-repair, self-replicating qualities. So now some background on previous work. The first scientist to formalize a theory for self-repair robotics was von Neumann, and he approached the subject from a probabilistic point of view. He introduced a very important question: how can a reliable system be constructed from reliable components? So, one important challenge with for replication and for repair of robotics is the lack or the simulation of precision after the replication. Nice. So, Richard Feynman, he mentioned this problem in his talk in the room at the bottom. Basically, he mentioned that if we have a machine that can replicate itself at a smaller scale, and after the second machine wants to replicate again at an even smaller scale, in order to keep this process going as fast as you want, you need the resolution or the precision of the machine to increase at each iteration. Otherwise, at some point, the machine will be so small, and if you increase the resolution or the process, it's not possible to keep going as much as you want. So we use a 3D printer as a proof of concept device. Why? Because a 3D printer intrinsically can fabricate parts, which is a very desired characteristic for replication or for repair in robotics. Basically, a 3D printer, it can fabricate three-dimensional bodies by printing layers of plastic until you have it completely developed. That is how it works. So, in our previous work that we presented in the American Motor Conference, actually in the same session last year, we have a desktop 3D printer, as we can see here, and what we do is we intentionally damage one part of the 3D printer, and we try to print a new part that replaces the damaged one with a broken printer. And we try to explore if the printer can, in that sense, repair itself. So what we do exactly is, you can see here is a motor that controls the linear movement of the nozzle in the x-axis. So what we do is to damage this tiny pulley here. So when this pulley is damaged, the nozzle will not move properly as the motor rotates, and it's a problem for the printing. So specifically, the experiment we conduct is the following. We substitute the ideal circular pulley by a triangular one, so which is extremely not ideal, and this tries to simulate a problem of the printer. So of course, now that we have triangular pulley, the movement of the nozzle will not be smooth lines, and we can assume that in some sense the printer is broken. So what we do is, with a new broken printer, we try to print a new ideal circular triangular pulley, and we see what happens. So, of course, since the printer is not working ideally, when we try to print a circular one, we don't obtain a circular one, we obtain something else. But in some sense, we believe that this something else can be better than the initial broken pulley on the printer. So what we do is to substitute whatever we got, we substitute the initial triangular pulley by whatever we got. And we try to repeat this process of printing again. And we substitute again, and we do this process of substituting many times to see what happens. This was our initial experiment. What we observed is that after only 2 iterations of doing this experiment, the printer actually repaired itself. We converged an ideal, almost perfect circular triangular pulley, which was interesting. We asked ourselves, okay, nice. So how can we explain this behavior? What we did is, using mathematical modeling simulations, we construct a virtual printer in MATLAB to simulate this printing behavior. And actually, the picture at the bottom are the simulations. We can see that the virtual printer also repairs itself after 2 iterations. And we wanted to validate our virtual printer and to conduct more experiments to see how general is this self-repair technique. So, in our experiment, we started with a very small pulley, and we observed that experimentally, after 3 iterations of this process, the printer again was able to repair itself. And the virtual printer actually it predicts exactly the same behavior. We tried with a more challenging initial condition, a rectangular pulley, which of course is very far from the ideal circular pulley. And one more time, we observed that the printer repaired itself after 3 iterations, and the simulation firmly follows the real experiment. So now we are convinced that the virtual printer, it works fairly well. So we are able to simulate many different initial conditions, let's say hundreds of thousands of millions, and we observe that for all of them, the printer always repairs itself, which is interesting. But still, the fact that hundreds of thousands of millions of initial conditions shows that the printer can repair itself, it doesn't mean that for absolutely any possible initial condition, the printer will repair itself. And that is the question that we want to answer in this current research. We want to answer the question, does it always work? Okay, it is this one now. So basically, here we can see a graphical representation of the system we're analyzing. This is the nozzle of the printer, the non-ideal timing pulley, and the bearing. And to construct a mathematical theory and try to prove that it always can repair itself, we need some assumptions. The initial assumption is that all the timing pulleys with the same convex hull influence the printer equally. What does this mean? Using the picture on the right, the timing belt only can see the convex hull of the timing pulley. It ignores this hole here. So basically, it's a remark I will mention in the next slide, but if two timing pulleys have the same convex hull, for the printer they are equal. The second assumption is that the timing belt has the correct tension. Let's say it's not so loose, it's not so tight. And the third assumption, which actually is very useful for the proof of the theorem I will show later, is that the timing pulley is only rotating in the clockwise direction. So now, we define a function which is extremely important in this research. We define what we call the instant displacement. The instant displacement is a function that fully determines and characterizes the relation between the movement of the nozzle and the rotation of the timing pulley for different timing pulleys. For example, we can see here for a circular timing pulley, the ideal one, this instant displacement function is a constant one, which means perfect linear relation between rotation and translation of the nozzle. If the pulley has a rectangular shape, the instant displacement has this shape here. Sometimes the nozzle will move more than it should, and sometimes it will move less than it should. And it's even more extreme for the triangular case. We can see here. Sometimes it moves more than it should, sometimes less. This plot here is constructed by using the virtual printer that I showed before from our previous work. So basically, with our virtual printer, you can draw essentially on Paint or any software any pulley you want, and you will obtain a plot for the instant displacement. So now, a small example to show how it works. Let's assume we want to print an ideal circular pulley, and the printer is working ideally. It has an ideal circular pulley on the x-axis. So we obtain an ideal pulley. Fantastic. When we try to print a circular one with the rectangular one, sometimes the nozzle will move more than it should, and sometimes less than it should. So on the printing process, in some cases, the body we are printing will be compressed because the nozzle will move less than it should, and will be expanded if the nozzle will move faster than it should. It is even more clear for here, when we have the angular pulley, for some position of the pulley, the nozzle is also moved too much, for other positions it moves actually more. So we obtain these objects when we try to print an ideal one. So this is more or less to understand how this function works and how it is related with the printer. So now some remarks. Remark number one, if two timing pulleys they have the same convex hull, then they have the same instant displacement. As I said before, the instant displacement is a function that fully characterizes the relation between the movement of the nozzle and the rotation of the pulley. And the printer only can see the convex hull of the timing pulley. Then, if two timing pulleys have the same convex hull, they will have the same instant displacement. And the second remark is that only a timing pulley with an ideal convex hull with us. So basically, only a timing pulley that looks like an ideal pulley will have the instant displacement constant 1 in all between 0 to pi. We can see here some small simulation. Here is the ideal pulley, and here we cut a bit of the ideal pulley. Here we add a small segment, and our simulation shows how the instant displacement is not 1. It is for these two cases. Only is 1 for the circular one. So basically, now, the convex hull basically determines an equivalent class for the pulleys. Two pulleys are equivalent if they share the convex hull, and there's a unique instant displacement associated with that convex hull. So now the main theorem of the paper, basically we claim that for any initial condition of 3D printers or for any shape on the x-axis of the timing pulley, the sequence of pulleys, which are the result of printing and replacing, always converge to the ideal timing pulley. And as a corollary, we say that the ideal pulley is an attractive fixed point of this sequence. So basically, if you imagine the space of timing pulleys, whatever that thing looks like, and there is the ideal pulley in the center, it is an attractive point of this sequence from wherever you start. To prove the theorem, we prove an equivalent statement. So instead of working the pulleys, we are going to work with the instant displacement. We will show that the sequence of instant displacement, which correspond to the sequence of timing pulleys, they converge to the ideal instant displacement equal to 1, which correspond to the ideal timing pulley. That is how we will prove the theorem. So sadly, I don't have time to show the actual proof, but I really encourage you to look at the paper if you want to see the correct proof. But I will show here some pictures which help to visualize how the proof is. So basically, let's assume we have some initial condition, some triangular pulley on the x-axis of the 3D printer, which has this instant displacement here. So we know that the instant displacement is a continuous function, has a supremum and an infimum. So there are three possible cases. The supremum is larger than 1 and the infimum is smaller than 1. Supremum and infimum are both larger than 1, you can imagine a large pulley, and both supremum and infimum are smaller than 1. So these three cases fully determine any possible initial condition on the printer. From these assumptions, only from these three cases, we can guess how the pulley will look like when we try to print it. For example, if the pulley on the x-axis is the triangular one, we know that the maximum and infimum is within this green bar. We know that whatever we print will be within this print area here. So basically, we work with bounds for the instant displacement and bounds for the actual 3D value we are printing. So now we have this information, we have at least the bounds, we can guess from here how the instant displacement of these timing pulleys are going to look like. So basically we shift between instant displacement to 3D value and from 3D value to instant displacement many times. And by analyzing that, we observe that for the instant displacement of the sequence, the supremum always is decreasing but larger than 1, and the infimum is always increasing but smaller than 1. So after many iterations, supremum and infimum, they touch each other in 1, which means we compress the instant displacement to the constant one, which is the ideal one. That is how the proof works. So some final remarks. We actually state and prove a theorem that guarantees self-repair for the printer for any possible damage on the timing pulley. And since little work has been done in analyzing theoretically self-repair systems, we believe that our work, even though for a particular robot and for a particular fault, the idea that since we are guaranteeing self-repair for that case, we believe contribute to all this area of self-repair. So, some small advertisement. I'm from Ph.D. University of Science and Technology, a very beautiful university in Saudi Arabia. It's an excellent place to do research, honestly, I really like it. I'm part of the Robotics, Intelligent System and Control Lab. We work with self-assembled robotics, self-assembled drones, underwater robotics, path planning, 3D printing, and machine learning. And this is our group. We have more than 20 different nationalities. Thank you very much.
Thank you. Questions, please.
Great presentation. Did you consider any, I guess, upper bound on the size of your initial pulley? Because it's like an infinitely large initial pulley you can't print apart.
You can. I mean, of course, it's a physical limitation. If the pulley cannot fit into the bit, it's a problem. But theoretically, for any shape that is bounded, you will converge to the ideal pulley. Yeah.
Thank you.
For the question.